All right, hello. We are back on stream. I am Junchan, and today we're back on the NBody simulation series using Haskell on the GPU. And we've actually fixed quite a few things since the last time. We still haven't managed to actually run the example code yet, but I think we're progressing and we're really nearing success here, and I'm really happy about that. And there's some additional goals that I've added here in the past streams, which is that I want to create a blog post, but more importantly, submit an issue to the Accelerate GitHub to explain how I went on with the Windows setup, and I've been taking pretty detailed notes about that, and that was a request from them on their website right here. If you're trying to install Accelerate on Windows, please let us know how you went, especially if you're successful, right? So these instructions will help others. And then there's even a stretch goal there, which is that if we submit an instruction, then in a year or maybe even less, it might be outdated already. So a way to keep things in check would be to contribute some CI pipeline. So that's a bit of a stretch goal. I think I want to definitely play with the NBody with Haskell on the GPU as well, right? But that would be a really nice thing to do. So where were we last time? So we fixed this problem about CU long. Basically, I think that actually also warrants probably some a PR, to be honest. So I'm going to put this here because that's something that's not too hard to do. PR on CUDA for the CU long errors. So I'm not sure why nobody had reported it, but yeah, that would be nice to do. And then yeah, there's this issue that's Windows related. I'm not sure whether I'm gonna be able to get into that. And right, so we have these install instructions and a couple of the issues that we encountered, definitely not formatted as a blog post or even a GitHub issue quite yet, but I'll review that as we want to post it. And yeah, what happened last time is that we were right somewhere around here, I think, and it sort of hung there for a while. And then basically I Control C that I killed it and then rerun it, and then it seemed to start building new things, but also this error message there, and that's an error message that I recognize. For some reason, Cabal seems to be I don't know, maybe it's related to the path. We were able to, we had this problem right here, but then when we ran Cabal install instead of Cabal run, then it worked. So it makes me think that there's something about the way that GHC or Cabal calls out to executables that somehow makes either calls onto the Win32 version of the executables in our MSys environment or something like that, because this error now is showing up again. So we were able to work around it by doing Cabal install and then running the executable directly. But now I don't think we're going to be able to do that because it seems like GHC is actually calling an NVVM itself. And the fact that this is a Win32 error here really makes me think that I don't know, that maybe we've installed a 32-bit version of GHC and Cabal actually. That would kind of make sense then. Huh. Since then after that we had a warning, and then we had another one of these exactly the same error message, and then it actually even failed with the stack trace. So yeah, so this could be nastier than I was letting go by saying that we might be able to run the example. Yeah, well, I hope that this stack trace is because of this. It's the same root cause as the Win32 error, because if not, then we're going to have some heavy stuff on our hand if the only thing we have is a failing compilation job with the stack trace. That could be a dead end for this particular attempt, or at least one where I would have to submit that to the issue tracker, not as a success, but as a well, almost success. Maybe we don't know how far we are from the goal. Okay. So first of all, how do I check whether the GHC we have is the 32-bit version or a 64-bit version? So what is possible is because we haven't installed GHC from the MSys registry, that doesn't look like the path that I was expecting, to be honest. Oh, no, it is. Yeah, it has the 64-bit info there, plus we needed to add the DLL, access to the DLL. And the DLL are obviously accessible in both 64-bit and 32-bit versions. But because we installed GHC with Chocolatey and not with the Ming GW64 environment, it's possible that we installed a 32-bit version. So let's find out somehow. Chocolatey Haskell stack. It's not, we didn't install Haskell stack. I think we installed Haskell dev something, right? That's inside our log. Haskell dev is I think the meta package there, or the virtual package. And some stuff didn't pass there for some reason. What was that? Okay, wow, that's a huge log. Okay, let's not look at that. Will it tell us? It doesn't even mention whether it's in order to facilitate package installation, a new command let Ming W64 package is created to make it easier to install native dependencies just as GTK. Oh. Interesting. Well, I never read that doc, and it seems like the package automatically configures MSys2 for use by Cabal if you already have MSys2 installed and nothing else needs to be done. Yeah, and it did install MSys2 for us, in fact. Yes. Huh. And so I could have done something like this then to install the packages instead of... so I guess that's interesting. That's an alternative path there, which is that we could have continued in the PowerShell somehow and did that. Okay. So I'll take a note of it. There, from here, there seems to be an alternative pathway described in blah with and I suppose we can put this also here. Okay. But I think I kind of like our way. I really don't mind being rid of the PowerShell and being instead in an MSys2 bash shell. Okay. But that doesn't tell us. So can we know somehow maybe just GHC version would tell us. No, is there a version verbose? No. Or maybe if I LD or LDD, I mean GHC. So let's do this and let's LDD. Yeah, Win32. So we have a 32-bit version of GHC. Okay, well that's good. We know why at least part of the messages, part of the things are failing. Turns out we have a 32-bit version of GHC, and we can even show what we did for that. All right, it's a different keyboard shortcut here, and why not put the whole thing? Huh? Okay, yeah, same shortcut thing. Okay, and yeah, I mean that's clear. So let's see, Chocolatey GHC 64-bit. GHC 9, 64-bit. So is that a new thing? So upgrading to 8.6 may be an option. There's no such thing as 64 on this page. CPU 64-bit. Okay, so the other approach, of course, is the package registry for MSys2 and see whether they build GHC there. And if so, it wouldn't be in the base packages, but they don't seem to. And we are then a little bit stuck. Okay, GHC 64-bit on Windows. Let's broaden our horizon. So okay, possibly Haskell platform could help us with that. Oh no, okay, what am I saying? 8.6 is before us. We're 8.8.4. So okay, prior releases. So it means that current releases will satisfy us. Well, they won't, because if that's the option, then we know. Okay. What about this? It's just listed as matching 64-bit. It's just a query. There's not even a. There's just a tag. Oh boy. Oh. No, that's not what we want. Oh, there's a full list of options and switches. And no 64-bit in there. Well, it looks like actually this this link isn't here anymore, so maybe documentation, see the docs, CLI, full list. Install. Yeah, no, that's not what we want. Checksum, doesn't matter. Oh boy, are we gonna have to build GHC? Is there no such thing as GHC 64-bit on Windows? I mean, we know there used to be, but there isn't anymore. Let's look at the prior version again. So this was, yeah, this was built by the Haskell team itself. But now that they try to hand it over. Okay, what if stack? Well, let's see what, because we do have stack installed, right? We do, and it's a 64-bit version. So that's in fact promising, because maybe stack would ship. So if we shifted to not build with Cabal but build with stack, then stack would install its own. I mean, we could tell it to install its own GHC, and then we have some chance there that maybe it will install a 64-bit version for Windows, because I think stack. Yeah, well, hopefully the stack folks. A little bit more kind of production minded somehow, but let's just which stack? No error. So we can't run LDD on it. We did install stack via the did we? We installed stack afterwards. I thought we installed, yeah, we did install it Haskell stack via Chocolatey as well, but that was a 64-bit version. Okay, so how can we find out? I think, isn't there a stack? Well, to be honest, the easiest way is just to copy the stack 8.8 is where we want to run, to stack.yaml, and then to run stack init. No, just stack build, I think. And okay, first I think it's just downloading stackage. And then we can find out if stackage for 884 so maybe that's not the resolver that does this. Let's keep this somewhere in sight. Windows 64-bit installer as well. Developing on Windows. So everything seems to converge on MSys2, so at least we didn't get lost on that account. Okay, so then some specific changes, but this is reassuring, right? They talk about Pacman. Oh, and you can actually stack exact pacman. So you can use stack almost as a wrapper environment. It's quite interesting. But then the question is, what does it do with GHC installs? The fact that it doesn't say anything and that it delivers a 64-bit executable, all of that is all positive signs. But I'd like to check. Maybe we can see here where the GHC versions are. Commercial Haskell, that's it. Yeah. Okay, sure. Okay, well, copy this link and trim it. And okay. Oh, well, oh, strange. 64-bit here, but Ming GW 32 here. 884 is what we would want, and same shenanigan. But you know what? That's also something we could install directly, in fact. Because now it's installing GHC 883. So at least we know that it actually installs. And now that I see that the default version was 883, it also makes me think that maybe that it's not impossible that our CUDA problems were linked to a change between 883 and 884. So let's just look at the Haskell GAC 884 changelog. Plugin process creation in Windows. LLVM backend. Oh, that's fairly old LLVM backend. So we'll have 2 Haskell installs, but in fact having stack is probably a really good idea. Long-standing bug gets, of course, and then some base library changes. 13 C changelog provided by these packages and no links. Yeah, old school. Base, but to be honest, then I want to check whether that's the same version or a different one from here. Okay. And HTML. And okay, I'm gonna read this note. Okay. We were in user guide. Okay. And 883. Oh, okay, I see. Well, now I know. Okay, I can't go up one level. I can. Let me do the previous topic at least. 4.13.0. So, yeah, base is where we had our foreign C related imports. So I'm not sure that this was related. So indeed, now we're going to, since we modified CUDA 10.2 for this compilation problem, then I wonder, well, we'll know soon. It's actually also installing MSys again. I'm fine with that. I think the whole point with Stack is this kind of sandbox environment, and I think it makes less and less sense on Unix, Linux style, or even OS X because of the new Cabal features. But in Windows, I think it still probably is a really good idea. Okay. Oh. Could it be that there's an underlying problem with okay, let's see. Package. So could it be that when we're calling out, then we use this Win32 API, and therefore and that's why we receive these error messages? We shall see. GHSQL library. Let's see what issues are related to this. Yes, failures. Uh-oh. Okay. Seems like that's a path issue here. Now in this case, I think it's not found. It's not that it's let's double check. Yeah, not loaded, and then access violation, but then before that also not loaded. And then the previous errors we had were with this NVIDIA query, and that was the same error, and I think that's really about not being able to launch a 64-bit library. But that was my interpretation, but maybe I'm wrong. Here, and yeah, that was right here. A bit higher up. So here, yeah, we try to do cabal run. And we fail with this. Command line here feels a bit like that's cabal telling us that it's launching a shell out or something. But then looking at what we had in our path, it looked like we had the right library. Oh, it's just that in that case, the library wasn't in the path. So then we add it in the path, then we run the cabal run again, and then exact same error. So it wasn't the problem with the path. But then if we install, then it completed, and then we were actually able to run it. Okay, I have a doubt. What if we didn't run the Haskell version here and that we ran the version that was in the path? That's totally possible. Okay, I'm going to start another shell. Okay. And make sure that we have that binary right here. What am I doing? We don't. I mean, yeah, clearly we don't. Is it in, where is it? Copying, well, yeah, the issue is that it's copying it somewhere. So I guess, let's try and find out where it is. NVIDIA device query. Right, that's because we haven't done a little path incantation, because I'm too lazy to try and figure out how to do this in a way that's sane. And whoa, what did I, what did I do to my path? No, path is, well, no, path is not great actually. Well, in fact, yeah, because where did I was supposed to add this, what we added at the top there. That was actually important. I don't, oh no, it's here. Oh yeah, so why did I added it? Hold on. Yeah, it is. So it is. Yeah, it is here. Okay, so let's try again. NVIDIA device query. Okay, Cabal bin. So no, so we were executing the thing we built. Okay, so no hallucination here. And so that was after running Cabal install rather than Cabal run. Thanks a lot for the pointers. Which pointers? Was that migrated somehow? Okay. Well, let's see where our Haskell install and is it building Haskell from source? It looks like it is. No, it's not. Okay. Oh wow, it's going pretty fast actually. Is it using my CPUs? Well, there's several GHCs running in parallel. That's one thing. Several Cabal running in parallel. Check this out. And I don't have a multi-core visualization here that I don't think. Logical processor, I do. Yeah, they're all fully utilized. So that's so much better than the chocolatey version. The chocolatey version was only using one of the, like the GHC. GHC was using, oh, well, I'm not sure I get it then. GHC is still using only 10%. And I would think that it would be using more. But there's some GCC threads, and I mean, Cabal is not consuming much. And I mean, there are several GCCs running at sort of between 3 and 9% here. So I don't know how. Or maybe in addition to that, there's another GCC. Hmm. I mean, it looks like there's definitely well, it's a little bit sort of a strange parallelization, because I would have expected JC to fork threads and that the JC runtime would take care of that, but maybe not. Maybe stack is parallelizing this somehow. Anyway, we're rebuilding the whole library. If it just works, then we can yeah, we can get rid of a number of these problems. Oh boy, what a bad decision at the beginning then to go for HPAC and not stack. Huh. Well, these things happen. Okay, so that's going to take a while. I'll take a little break and I'll think about what to do. We'll probably read more about Accelerate and its programming model. I'll be right back. All right. So apparently we've got a new problem on our hands. What is that? Problem when trying to compile OpenGL row. Is that or is it here? While building package regex posix. Scroll up to its section to see the error. Yeah, I guess that's the inconvenience of having several GHCs running at the same time. Regex, right. Regex, POSIX. It's ignoring its bounds. Interesting snapshot of a Cabal file dependency information. N. POSIX. Okay. What? Okay. Right, so should be close to here. Yes. Fatal error regexh no such file directory. That's not a good sign. Oh boy. Doesn't want to copy paste because I'm in this different mode, I believe. And then it throws me somewhere else, so I can't find it anymore. Okay. Yeah. That's where the error is. And can I exit? Here. Yeah, it's a bit ridiculous. Okay. Good. Header file is missing. Yeah. Wow, that sounds like a bit of a of a dirty workaround. I was gonna say, okay, that's no. Right, that's good. That's good. So we can do the stack install thing, or is there even a way to do this? Oh. Okay, so it sounded like this could solve it, to add this into the stack file, but then someone seems to claim afterwards that it doesn't. And if we set this flag to true, well, if we take this text to true, then I guess we go here. So this shouldn't execute. But maybe there's a problem with this clip. Okay, let's try with modification of the stack. What did I do with? Here we go. So, right, would be an accelerated example, and now we have a stack of YAML, and we're saying what? Saying we have some flags. Okay, well, I suppose we can try that. Regexposix clib. Seems installed. Now let's keep an eye on regexposix. It has been reopened. Okay. Is that better? I don't remember which step it failed on, but at least it's going. 6, 7, 7. Configuring, installing, registering. I think we're good. Yeah. Well, that's good. That's something that's fairly easy to contribute back. Okay, so while this compiles, I think, well, none of that stuff is actually interesting now. We actually captured it in our previous links. And I'm thinking, in fact, pretty much the whole thing. Except maybe I should have kept that last window just to reference it. Yeah, I think I should have done that. So let's go fish for it. This one. Because we want to reference it if we submit a... So we kind of, yeah, we've kind of forked again. Alternative pathway. Now we take in another alternative pathway. Shoko install Haskell stack is fine, but yeah, it looks like we need to sort of start again, huh? So send PR for stack 8.8.yaml. these guys. Okay. It's keeping on, so let's leave it be, and let's go to the examples again. It started taking a look. All right. At the examples and at the code, but definitely worth taking another look. Examples and NBody, and I could totally do that in well, except that yeah, this will close all the time, right? So that's going to be supremely annoying. So yeah, right. So if I remember, run interactive was sort of the top level function together with play, and it called simulate advance with advance on one hand, which is the simulation loop, and that used in turn the solver, which chooses a different solver which is passed as configuration, and the solvers are able to run either on the GPU or on I'm making this mistake again, or on the CPU. So the naive one, for instance, has some if-defs. Oh no, this one actually is not even accelerated. How about naive 2? Neither. And this one neither. So right, no, I'm mistaken here. That's not going to be accelerated. What's accelerated is advanced bodies, I think, then, which I think is in common, maybe in world. Oh right, no. What defines whether it's ran in the CPU or not is not this, it's backend. Which is an option, and how does it get evaluated? OPT backend is fine, but uses the backend on the run function here and on run one function here, and backend. Well, is there a backend? It's not here. I think it's in the. It's actually in the library here. Internal. Maybe not. Oh, backend. Right, that's it. And this passes the whether it uses CPU or PTX, which is the GPU backend. And yeah, right, run and run one actually come from this package, and default backend comes from this package. Okay. So this is really more low level inside the belly of the Accelerate library, but I mean, we might spend a little bit of time there, but let's look at what solvers are, because the advancing bodies, that seemed fairly straightforward. Let's look at it again. But it's this equation of gravitational pull between body I and J, and it looks like the physics, you know, gravitational constant and square of the distance, inverse square of the distance, and some normalization and the product of the masses. It all makes sense. And then some kind of derivation for right, because this is ij, so you need to integrate on j in order to get all the forces applied to I. So sum is an integral of I, it integrates over j. And so that's the formula. But then, then there's kind of singularities if is that, well, were they too close to each other? Is that right? Because then this grows to infinity. So we want to avoid that. So we add an epsilon, a softening factor. And then, and so, yeah, right. That doesn't matter. Softening factor models the interaction between two Plummer point masses, bodies that behave as if they were spherical galaxies, and thus mass may pass through each other. Ah, right, okay. Oh, because it's actually it changes the exponent there. Interesting. Okay, fine. So that's the final equation, and then it's modeled. Well, that's a little bit unfortunate, but so advanced body ends up being okay, acceleration, which is same as the force, with the smoothing parameter epsilon, point mass, which is a vector position plus a vector of velocities, I believe. I think we had let's get out of this, back into the examples, and common type. Point mass is position. No, it's position and mass. A body adds the velocity to it. Okay, and so we're saying that we have 1 point mass. Right. Okay, that makes sense because it's saying that, you know, it's not that we don't care about the point mass, but it's that when we calculate the acceleration on a given point mass, its speed doesn't matter. Like gravity doesn't care how fast you go. It's kind of a snapshot. It influences how fast you go, but it doesn't care how fast you go in order to know how much it's going to decelerate or accelerate you. It only cares about how distant you are and what the masses of the bodies involved are. Okay, and then so the point being accelerated and the neighboring point, and that returns an acceleration. And so we say that the result is s to the power of r, and s is mj times inverse 3. So inverse 3 is 1 divided by the square root of r², which is dot rr. So that's the dot product of r's. Oh, right, r being the difference between the position of PMJ and PMI. So our 2 points. So r is the distance between the two. We do a dot product of this thing, so multiply pointwise the vector to get our square. Then we add our epsilon square, epsilon side epsilon. So that's this parenthesis. Then we divide it by the square root, which means that we exponentiate it to a half. And then we cube it, and we get to 3 here. So 3, the power of 3 of a half is 3 halves. And then we then what do we do? Then we multiply by mj, which is the mass point of mj, which is that, mj. And so now we just have to multiply it by r again. And we are done. I don't know why, though, it's a multiply upper thing. Oh, because s is a vector and r is a scalar. So this is a vector and this is a scalar. Is that right? No, it's not right. Actually, the dot product is the multiplication pointwise, and then the products, and then the addition of all the elements of the vector. Yeah. So no, this is actually. So what is this? Google. A2FA, compute the left scalar product. So what's on the right is a vector. What's on the right is a vector. So r, oh yeah, of course, yeah. Dot rr, all of this stuff sums up to a scalar, but r itself does not. R itself is a position difference vector. Okay, so that's this thing, and then we need to sum it and then multiply it by h mass. So how are we going to do that? Haskell is used where? Well, I see Haskell of body, but where is Haskell used? Is it just exported and then used somewhere else? Yeah, it looks like it is. Interesting. So when we run advanced bodies, we don't use Haskell. We only use Haskell of bodies, and Haskell of bodies is view. That's a lens into the third element of body, and bodies have acceleration as their third tuple member, but Okay, yeah, that's fine, I suppose. So advancing a body forward in time is to, given a time and a body, to lift PM prime, which takes the position, which is position in time plus the velocity. Velocity is the velocity plus the time times the acceleration. That makes sense. And then the new okay, where is PM? Okay, PM is used to calculate the position of mass, position of point mass, which gives us pos. Okay, and then pos is used for adding the velocity and the acceleration, and then give the mass. That's all good, but that seems like that's... Oh, right, that's actually advancing the body given a previous position, velocity, or point mass, velocity, and acceleration. It doesn't modify it doesn't exert a force on the body. This is just a body free flying with a given given acceleration. So I suppose that at some point we need to map over or pass it acceleration. So maybe that's advanced world that does this, or maybe that's the solver that does this. Because what do we pass to advanced body? Well, first of all, it's advanced bodies. It's not advanced body, and that's probably where the smarts go. The smarts happen. So advanced bodies is defined in common world, and indeed it imports common body, and from that it uses Haskell somewhere, right? Not Haskell's. Oh, was it? No, not Haskell's. Define calc Excel. What is that? Do we have calc Excel here? We don't. We just have Excel. Where is calc Excel? Is oh, it's passed to advanced bodies. Oh, okay, right. Oh, so this, okay, the solvers use this. Okay, the solver used the formula, the Haskell formula, and then the naive. Well, let's take a look at the naive one version. It might help us understand. Just takes this epsilon and a vector of point masses, so all of the things that are flying over, and let's keep an eye on our compilation. Okay, yeah, I think that that's probably the error that we encounter. Yeah, it's the same error. Okay, so we'll solve it in the same way, but let's stay a bit with the code, right? And what time is it? Okay. So, right, it takes a vector of point mass, which is all of the bodies flying over, and then returns a vector of accelerations. And then we can, when we have that, then we in main, yeah, we pass the epsilon to it, and then we pass this calculation to advanced bodies, and advanced bodies, given that calculation and a time step, transform the vector of bodies into a new vector of bodies. Okay, yeah, that makes a lot of sense to me. That's the glue, and the glue, just to check how it's done, is that the acceleration uses calc Excel, so and calc Excel is going to be taken from different solvers, and it applies it to mapping point mass of body to the bodies, right? So that's going to, bodies have point mass, velocity, and acceleration. Here we're only going to get the point mass of them, which is where we need to pass it to calc_accels. And so we'll do it for each body, and then we'll apply those accelerations with the zip width and advance. And zip width, right, is, okay, yeah, that makes sense. Zip width is just going to be taking the bodies and create a tuple out of the result of body and accels. And in bodies, we're going to have each body that will be incremented by a given time step, and then we'll set the acceleration that's coming from the accel that we calculated here, and modify our bodies to include that. And so in the end, we'll have vector bodies again. We'll reconstruct our vector bodies. Okay, lovely. So then calc_accels in the naive version, just, and by the way, just as a reminder, because all of this happens in the ACK monad, all of this gets basically statically analyzed, and then rules are applied to make the code really efficient, and find loops where they can be, find ways to lay out the data where it's going to be best laid out for rapid consumption by the CPU and caching and pipelining and all these things, and maybe prediction. Now, branch prediction, I don't think is part of this. I think, in fact, that's one of the things that is explicitly not part of the flat data parallelism approach that Accelerate uses. And right, so calc_accels then does its calculation, and what it does is that it takes this epsilon and passes it to accel, and does basically just a fold. So the idea being that with a vector of point mass, we get back a vector of acceleration. So for each point and mass, we know we sum the acceleration over all of the other bodies. So the fold here sums starting from 0. So we start with a body that's that hasn't had any of its interactions calculated, so the acceleration that it's being subjected to is 0. And I guess we mean really the 0 vector here. I think this must be, I think we mean the 0 vector, and that plus is actually also a lifted plus to the vector, to the vector plus, I think. And then we seem to be considering that there's rows and columns of particles. That's interesting. So I guess that's the way that we manually lay them out. Let's see what the command says. Calculate acceleration of these particles in a naive O(n)² way. Replicate the bodies out by rows and columns. Zip them together to get all interactions. And then perform a parallel reduce along innermost dimension to get the total contribution for each particle. This relies on array fusion to combine the replicates into the body of the reduction. Otherwise, we quickly exhaust the device memory. So in fact, what we do then is we replicate. So if we have 1,000 bodies floating around, actually we replicate 1,000 bodies in, and we have them in each row. We have those, such that then we calculate acceleration at each step by right, zipping them to get all interactions, and then doing this parallel reduce here. Along the innermost dimension, which I suppose is the row, I think. So that's a way to, that's the shape of the replicate, of the accelerate vector. Is that right? Let's look at the accelerate. Or maybe it's array. It's the shape of the replicate. We have C slice and replicate for examples. Oh boy. That is sad. I mean, you know, it's sad that a programming language community that prides, that, you know, has the, is it the, that, am I saying this correctly in English, that prides itself, I think that's correct, right? To, you know, think about correctness, can still not have like a link checker on their documentation generation. Okay. Right, so replicate does take an array with a slice shape. Ah, slice shape. So I think that's why we have those alls here that I actually hadn't seen yet. Can the replicate. Right. A marker for an entire dimension in slice and replicate descriptors. So here the slice shape is what allows to have an all. And so we're kind of only giving, it's interesting, right, this pattern, like here. We're giving it, so I think this is a const list of dimensions, but reversed, I think. It's usually you'd have the z at the end, but I think it's doing it the other direction. So you start with the 0 dimension array, and then that's the 1 dimension array, and then it's its first dimension, it has n, and then you say all, and then you specify all in the first and then n in the second, and then that's somehow that's going to fill out the entire array. I mean, I can picture it in my mind. It's really smart. I don't know why you wouldn't want to do ZNN bodies, though. It seems like that would be equally doable. Let's try and understand what's up. Yeah, all indicated dimensions into which the array's existing extent will be placed unchanged. Replicate an array across one or more dimensions as specified by the generalized array index provided as the first argument. Generalized array indexed index. Huh. So actually, this is an EXP. This is an EXP SLIX, or a slice index. And then the bodies is this array of slice shape, which I guess that the shape of which is inferred by the, what is it called? The generalized array index provided as the first argument. So I guess that it means that we don't know exactly what shape it will have at this point. We don't know exactly what shape it will have at this point, but then the compiler is smart enough to, then when it knows that it's combined, to infer the overall shape. Maybe. Because n is the size of the bodies, so yeah, that makes sense. Still don't understand why we couldn't do n. Like that, it seems like there should be a replicate of a replicate for two-dimensional arrays somehow. But maybe there's a type level complexity, which means that it has to be done that way. I don't know. Let's look at the example. Given the following vector blah, we can replicate these elements to form a two-dimensional array, either by replicating those elements as new rows, like this, constant z4. So we create an array of which the first dimension is 4, and the second is all. And so that just means 10. Or as column if we do it the reverse way. So it's a kind of a... Oh, right. Okay. No, now I get it. All right. So yeah, it's laid out differently. It's actually a transposed here, like calls is transposed rows. And so then if we have then how will ZipWiz work with arrays, I guess, is one of the questions. I mean, it will do pairwise, so it will be going through elements. I need to look at the type of ZipWidth. Do we have it here? ZipWidth. Apply the given binary function element-wise to the two arrays. We have x's and y's, and if we plus x's and y's here, we get the minimum, the intersection of the extent of the two source arrays, right? So it's like they're masking each other, and then we do, pairwise application of the, right? So in our case, we have n by n, but they're transposed, so they match, they have the same extent. And we apply XL epsilon, and so that becomes the I and the J, and we have all combinations in the, how do you call this? I always forget the name of this. It's like a network growth effect, or like transaction cost. I forget. Like Wikipedia. There's a doesn't I put this? Transaction cost probably to not. Yes, this. How is this called? So network effect is one way to call it, but isn't that the name of someone there? Metcalfe's law. That's it. Metcalfe's law. Yes. Yes. So because this is in effect what we're doing, and that's an n square problem, and I think we are basically with that those overlapping transposed arrays, we are connecting all possible pairs. Is that what's happening? Yeah. Well, we're connecting all possible pairs, and then we sum them across one, so that basically each row gets each row gets the value. So if we look back here at the transposed arrays that we were seeing earlier, where are they? Yeah, this one. Now we have body number 0, body number 1, body number 2, and body number 0 is going to be matched with body with itself, and then all of the other bodies, and then that's going to then be plussed. So each element of the array is going to contain the force applied regarding to 0 and all of its possible neighbors, and then the arrays are then plussed together, defining the sum of the acceleration impacting the body number 0, which is this plus, and it's a vector plus. And to convince ourselves of that, let's check the type of plus, actually, because there must be a plus defined somewhere here. There's a plus plus, concatenation, addition, sum. Sum of elements, and does it have the plus? Plus is not exported, so maybe it's Is this just an instance of that for num? Is it that is just that arrays are instances of num? Numeric type classes. Yeah, that's the case. Arrays are instances of num. So that means that when we use plus, we do pointwise plus, and we can do it to vectors. And so yeah, so because each element in our array, in my example, are in fact point masses, right? So it's three-dimensional vector together with a mass. And Haskell is able to use all of this and combine it into a three-dimensional vector, which represents the acceleration now. So we move from position and mass to now an acceleration, and then we have basically a transposed vector or just a vector of all of the accelerations for all of the points. Okay, so that's the naive thing, and we understood it. Fantastic, congratulations. And it's the 9:30. It's 9:30 now, so I'm just going to do what I think is done by doing this, and it's CUDA-0.10.2.0. And I think by doing this, we're going to compile with our new stack. Maybe not. Same package name is using multiple local packages. That's because then we need to comment this out. And that looks good. All right. So I'm gonna leave it here for now. It's good, you know, while things compile, we do some thinking, and I'm happy about my current understanding of the naive algorithm and how to do some accelerate. I mean, I couldn't write it, but I could, you know, read it and maybe write it a little bit. Because the abstractions that I use here are actually fairly well, they map the machine fairly well, so it's just arrays of stuff, right? I mean, there's some interesting complications related to these shapes there, but it's well documented, and I'm getting it. So we'll look into the other solvers next time. So that'll be next Tuesday, yeah, then I'll tell you how this stack build went and whether we've actually completely deprecated this old path. I mean, you know, we fixed the CUDA thing, so it's not nothing. And but it seems like all of the library problems could have been solved in a slightly more idiomatic way. And that means that, in fact, our blog post is going to be, and our issue is going to be much shorter. And that's fantastic. We, as a software engineer, we should like to have less stuff, less code or less documentation. You know, if it's well written and easy to understand documentation, right? And well written and easy to understand code. We're not talking about, you know, one-liners that are too difficult to understand. But if it still shrinks the size of the code, then it means that it's easier to think about, and that's a great thing. So I'll leave you with that, and I'll see you tomorrow for some pure script, and have a wonderful evening, and see you later.